Hello, this is Dylan Chung, and this is my Physics 2212 Lab 3 Magnetic Field of Permanent Dipole Magnets. The purpose of this lab is to examine magnetic field variation with distance from the bar magnet and evaluate the observed measurement against distance dependency shown from the Biot-Savart law. The model is a bar magnet modeled by GlowScript, and a quick preview of the results. Magnitude of the magnetic field increases with decreasing distance. So the closer it gets to the bar magnet, um, the greater magnitude the magnetic field. So the calculated magnetic fields for experimental was 8.173 times 10 to the negative fifths, and our theoretical was 1.976 times 10 to the negative 5. And the bottom left two images show our experimental data and our model on GlowScript. The fundamental principles we'll be using in this lab is the Biot-Savart law and the distance-dependent formulas for the bar magnet. These are the conditions. Our system is the bar magnet, our surroundings is the Earth, phone, and any potential source of magnetic fields. And our initial conditions is that the magnet is placed on the true east-west axis. Here's our experimental data that we took during the lab, and we could see from our chart that we have a slope of negative 3.1453, and the intercept is negative 14.603. So from this, we are able to calculate the magnetic dipole, and the work is shown on the right side, and we get a value of 2.4255. The observations that we see during this experiment is that when the magnetometer is far from the magnet, the magnetic field is close to zero, which was observed in the x direction. And when the magnet gets close to the magnetometer, the magnetic field in the x direction is increased. Looking at our GlowScript code, we plug in the magnetic dipole that we calculated and put in the line 24, and then we set a magnetic dipole moment and R vector on line 33, and then we can call this method several times, 2 on the same axis on the R vector, and then 4 on the perpendicular axis, and 1 on the angle of 45 degrees. Looking at our results, first off, our experimental versus our theoretical. Our experimental shows 8.173 e to the negative 5, and theoretical magnitude is 1.976 e to the negative 5. So we can see here clearly that our experimental magnitude is much greater than our theoretical magnitude. And the reason for this is that there may have been some potential sources of error, such as external electric fields, as well as shifting of the magnet or the magnetometer. And on the right side, the image shows the magnetic fields from the bar magnet. From this simulation, we could see that on the parallel axis, the field is much greater than the magnetic field on the perpendicular axis. So what if we hadn't laid our experiment to compensate for magnetic north and had instead laid out our meter stick at some intermediate angle with respect to Earth's magnetic field? So what changes is that the x and y component would change because magnetic north contributes to both components, and it's dependent on the angle difference from the true north. So what if we were to stick two identical magnets together and end to end and run the experiment again? We would see that the magnitude of the magnetic field would increase with combined magnetic fields due to superposition of the bar magnets.